Welcome, guys. So last time we went over the discrete probability distribution, binomial distribution, and the negative binomial distribution, Poisson distribution. We saw a number of examples, and today we are going to see the exercise problems. Because of limitation of time, it was not possible to go over the exercise problems last time. So today I would like to go over a few of the problems, and then after immediately we can switch over to the next chapter if it is possible, that is the continuous probability distribution, some continuous probability distributions. Okay, so first of all, let's see this problem number, we can say this one. So some problems are here. Problem number 5.49, the probability that a person living in a certain city owns a dog is estimated to be 0.3. Is estimated to be 0.3. Find the probability that the 10th person randomly interviewed in that city is the 5th one to own a dog. 10 person randomly interviewed, that means your x equal to 10, and your success rate, you can see over here, your probability is 0.3, and your k is nothing but, you can see over here, that is equal to 5, because 5th person, right? Find the probability that the 10th person, so 10th person randomly interviewed in the city is the 5th one. Okay, so that is the out of success rate. We are taking one particular number, that is k, 5th one to own a dog. Okay, so let me just share my screen with you. I wanted to share a screen with you. I'm sorry, I just forgot. So let me just share my screen with you. This is the thing I wanted to let you know. The probability that a person living in a certain city owns a dog is estimated to be 0.3. Find the probability that the 10th person randomly interviewed in that city is the 5th one to own a dog. So again, my p equal to 0.3, my k is equal to 5, and x is 10. So I can use the negative binomial distribution over here. So let me stop sharing this one and let me go for my whiteboard. So let me share the whiteboard with you guys. So I can say like this, that exercise number 5.49, it says that using the negative binomial distribution by, I would say, negative binomial distribution, we have b star, as you know, that is denoted by b star, and here it is x is equal to 10, k is equal to 5, and 0.3 here, semicolon, and that is equal to, you know, this thing, that is equal to, what was the formula? If you want, I can give you again the formula, because we went over all these things. So formula is something like this, that b star of x and k and p, that is equal to x minus 1 c k minus 1 and p to the power k and q to the power x minus k, where x is nothing but k, k plus 1, dot, 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 k plus 2, dot, dot, dot. So this is the negative binomial distribution, and we are using that distribution over here. So if you use over here, my x is equal to 10, as I told you, k equal to 5, and p equal to 0.3. Plug the values. X minus 1 means 10 minus 1 is 9, 5 minus 1 is 4. Probability is 0.3, 0.3 to the power k is 5, and q is nothing but, you know, this thing, that p plus q is always equal to 1. So naturally q is nothing but p, q 1 minus p. So that is equal to 1 minus p. 1 minus 0.3 is equal to 0.7, and 0.7 to the power x minus, or 10 minus 5, that is equal to 5. And if you use this one, that 9c4, that is equal to 9 factorial, or 9 minus 4, that is equal to 5 factorial, and 4 factorial, and 0.3 to the power 5, and 0.7 to the power 5. This 9 factorial can be written in the form of 9 times 8 times 7 times 6 times 5 factorial. This 5 will get cancelled out. 4 factorial can be written as 4 into 3 into 2 into 1. So you can see over here, this 4 2s are 8, and then after this 2 and 2 will get cancel out, and here it is 3, and here it is 2. So whatever the numbers are left out, that is equal to 9 into 7 into 2, and here it is 0.3 to the power 5 and 0.7 to the power 5. If you use your calculator, you're going to get that is equal to 0.0515. So this is your answer. So that's how you can solve the example, the given example. Now I would like to go for the next example. The next example is like this. Let me again stop sharing this one and let me share my book. So book says that find the probability that a person flipping a coin gets a third head on seventh flip. Third head on seventh flip. Please guys try to pay attention. Third head on seventh flip. That means my x is equal to 7 and third head means k equal to 3. And if you have a coin, the probability is not given to us, but you know this thing, if you flip a coin, that means probability of getting head is 1/2, probability of getting tail is 1/2, right? Because there are two outcomes, right? So my n is equal to 2 and each are equally likely to occur. That means my probability is 0.5, or you can say 1/2. 0.5, or you can say 1/2. So that's how you can work like this. So my second part of the problem, that is the first head on the fourth flip. The first head on the fourth flip, that is here you can use the geometric distribution, because first head, your k value is equal to 1. So no need to write. So that's why you can use the geometric distribution. Otherwise, you can work with 1 and you can use the negative binomial distribution to both are same. But whenever k equal to 1, at that time usually we go for the geometric distribution. That's what we decided last time. So let me go over this example. Just keep this example in mind that we are looking for the third head on the seventh flip and the first head on the fourth flip. Okay, so let me stop sharing this one, and again I'm going to share my whiteboard, and my example or my solution is like this. Let me change the color just to make you a little more convenient. So I would say that example number 5.50 says that using the binomial, negative binomial distribution, we have b star of 7, then 3, and then as I told you that probability is equal to half, or you can say 0.5, and that is equal to 7 minus 1, that is equal to 6. 3 minus 1, that is equal to 2, and probability is equal to 1/2. My k value, that is equal to 7. Am I right, guys? My k value, so that is equal to 7. So naturally, actually k value is equal to 3. So you can write here 3, and here it is k. I wrote it down directly, but if you want, I can write it down. 1 minus 1/2, that is equal to q. This is my p and this is my q. And here it is 3. And here it is, I have 7 minus 3. So actually that is equal to 6c2. And because my base is same, so I can just add the exponent. So it is 1/2 to the power 3 plus 7 minus 3. So that is equal to 7. And again, you can use this NCR formula just like the previous example, and you are getting the answer. So that is equal to 0.1172. I counted this part. Okay. And my B part, this is my A part. The B part says that the geometric distribution, why geometric distribution? Why geometric distribution? Because my k value is equal to 1. So it says that the first head on the fourth flip, that means I'm going to write, you know, the geometric distribution. Let me just recall this geometric distribution also for you guys, probably helpful to you. The geometric distribution that is given in the form of g of x and p, and that is actually nothing but b star and x semicolon, but you have to have your k value 1, and that is equal to p. So that is equal to gxp, and that is equal to p and q to the power x minus 1. K and k x minus k, but k equal to 1. So this is my geometric distribution. So I'm going to use this geometric distribution over here to get the answer of the second one. So it says that is equal to g of 4 and semicolon 1, 4 and semicolon 1. So that is equal to p is equal to half, q is equal to again half, 1 minus half, that is equal to half, and here it is 3. So that is equal to 1/16. Very easy. So you can get this answer like this. Okay. Then after, let's go for the next example. My next example, that is Again, let me share my book. Next example I would like to take, which example? I think let's go for 53. 53 says that an inventory study determines that on average, demands for a particular item at a warehouse are made 5 times per day. 5 times per day. Please keep this thing in mind that we are given 5 times per day. 5 times per day means it is a time interval given. Some time interval means we have to use the Poisson distribution. What is the probability that on a given day, this item is requested more than 5 times? Means probability of X strictly greater than 5, strictly more than 5 times. Not at all. Not at all means X equal to 0. So we are going to solve this example now. Okay. So now I would like to go for this example, and this says that 5.53. Example number 5.53 says that A part, that probability of X greater than 5, right? Greater than 5 because it is more than 5 times. And that is equal to, you know, this thing that is equal to small p and X and 5, X semicolon 5, and X runs from more than strictly greater than 5 means 6 and onwards. So 6 to infinity. And this can be written as 1 minus summation of probability of X and 5, and X runs from 0 to 5. X runs from 0 to 5. You can use the table over here given to you in the back of the book. I can show it to you, and that is equal to, let me just show it to you, and then after, let me again go back and show it to you. Probably that will be more useful to you. So let me just stop sharing this one. It's hard every time to go for this one, but it's okay. This is my book, and this is the page number, I would say. What is the page number? 165. Okay. And this one is given on which page? It is given on the page we are looking for the Poisson distribution, and Poisson distribution that is given on page number 730, 732. So let me go for this one, 732. Let me show it to you. Page number 732. Okay, look at here, guys. This is the Poisson probability distribution. My value was, what was my value? My value here, that was summation Px5, and X runs from 0 to 5, means my R value is 5. So always try to look at the R value. R value is equal to 0, 1, 2, 3, 4, and 5. R value is equal to 5, and X and what is that? R value is 5. R value is 5, and then we are looking for exactly at 5. So R value is 5. Here it starts with 5.5. R value is 5, and my P value is also 5. So R value is 5. R value is 5, and my lambda t is also 5. Okay. So actually T equal to 1 day and lambda t. So that is equal to 5. So let me do like this. Let me go for the previous page. You can see over here on this page, probability distribution R equal to 5 and R equal to 5, and look at my cursor, and my P equal to 5, that is 0.6160. 0.6160, right? 0.6160. So let me use this value. Look at here, guys. Let me use this value. That's how you can use this Poisson distribution table. The Poisson distribution table. There are 3 pages, 2 pages, I think 2 or 3 pages. 3 pages, 732, 733, and 734. These 3 pages, they are for the Poisson distribution tables. So one has to take the printout of this one. So it would be really very convenient to you. So that's how you can see this one. Every time I'm not going to open this book, this table, but you can see like this, my R value, summation R value, and that's what I would like to show you. Okay, so let me share my whiteboard again. So this is my R value. Look at over here. This is my R value. So this is my R and this is nothing but my lambda t. Actually, my lambda is equal to 5 and t is equal to 1. So that's why lambda t that is equal to 5 times 1 and that is equal to 5. So that's why I use this one. So x lambda t. And this x lambda t, then definition says that once you have this x lambda t, then after you can directly use the table. You don't have to go for the definition. The definition for Poisson's distribution we saw last time, that was equal to x and lambda t, that is equal to e to the power negative lambda t and lambda t to the power x divided by x factorial, where x runs from 1 to 3 and so on. 1, 2, 3 and so on. So this is the definition, but we are not going to use this definition. We are not using the definition. We are just using the tabular form. So by table, I would say A2, yes, A.2 or A2, page number 732 to 734. So here you can write that is equal to 1 minus what is the value? I just figured it out. That was R equal to 5 and 0.6160. So 0.6160. 6160. Same way you can use the binomial distribution also. You don't have to count the binomial distribution every time, but you have the table for binomial distribution, and that is given before the Poisson distribution in your book. And the page number, I would say, page numbers are 726 to 729. So use the binomial distribution, don't count it, but use table like this. It's easy. Okay, so once you have this one, then you're going to get that is equal to, so your answer for this one is equal to 0.3840. 0.3840. So that is the answer. This is my A part. Same way I can go for B part. B part says that probability x is equal to 0, right? Because why x is equal to 0? It says exactly not at all. So x is equal to 0. X is equal to 0. That means that is equal to P 0 and 5. P 0 and 5. You can use the definition or you can go for the table R equal to 0 and this one. So naturally I can write the same thing. That is equal to 0.006006 and 7. 0.0067. So that is the answer. Here you can use the this definition if you want. X is equal to, suppose 0. X is lambda t equal to 1. This is 5. 5 to the power 0. So here you can write e to the power negative of 5, and 5 to the power 0 is simply 1, and divided by your x value is 0 factorial. 0 factorial is 1. E to the power negative 5 is this value. 1 over, that is equal to 1 over e to the power 5, and that is equal to this value. So this is your answer. So that's how you can solve the examples. Let me save this page in a folder. And then after, let's go for the next example. That is, okay, let me clear all this drawing and stop sharing. And again, I would like to go for the book. Book says that my next example is, now let me go back. I don't want to open this one. I cannot every time, right? So let me use this one and page number 165. Okay, so page number 165. It says that, which example? I think we can go for 5.56. It is again a nice example. On average, 3 traffic accidents per month occur in a certain intersection. What is the probability that in a given month in this intersection, exactly 5 accidents will occur? Means probability of x is equal to 5, right? Exactly 5 accidents will occur. Good. I will let you know how to solve this one. Exactly 5, when you are using Poisson distribution and exactly 5 occurs, that means you have to start with 0 to 5 and then subtract 0 to 4. Means you're going to get exactly x is equal to 5. Okay. Second part, fewer than 3 accidents will occur. Mean probability of x strictly less than 3, because strictly less than 3 accidents will occur. At least 2 means x, at least 2 means 2 or more than 2. So x greater than or equal to 2. So probability of x greater than or equal to 2, that is equal to, that is my third part. Okay. So let me start with this one. Again, stop sharing the book and let's start the whiteboard. Okay, so my whiteboard says that probability of question number, okay, example number 5.56. 56. Okay. On average, 3 traffic accidents per month occur in a traffic intersection. What is the probability that in a given month at this intersection, exactly 5 accidents will occur? Exactly 5 accidents will occur. Let me start like this. That means that is equal to small p. Exactly 5 accidents will occur means 5, and on average 3 traffic accidents per month. Per month means time interval. Time interval means Poisson distribution. You know this thing. Now, whenever you are looking for exactly 5 at that time, what I would prefer, I would like to go like this, that p x3, where x runs from 0 to 5, minus p x3, where x runs from 0 to 4. You know that here you have 1 to 5 accident, 0 to 5 accident, and here it is 0 to 4 accident. So if you subtract, if you take 0 to 5 and then if you subtract that 0 to 4, that means you are getting exactly the 5 accidents like this. And here you can use your Poisson distribution table and you're going to get the answer. So that is equal to, let me write it down directly. So that is equal to 0 point, here I got the answer 008. This is my A part. My B part says that probability of x strictly less than 3. Probability of x strictly less than 3, and that is equal to probability of x less than or equal to 2. Less than or equal to 2. And probability of x less than or equal to 2, that means that is equal to, again, summation x is equal to 0 to 2 and probability of x and 3. And that means that is equal to, you're going to get, that is equal to, again, some answer. Here I found the answer. That is equal to table A2, 0.4232. 0.4232. Okay, then C part says that at least 2 accidents will occur. Actually, at least 2 accidents means probability of x greater than or equal to 2, that is equal to 1 minus probability of x less than 1, and that is equal to, that is very simple, x less than 1. So that is equal to 1 minus summation of x is equal to 0 to 1, and here it is probability of x and 3, and that is equal to whatever you're getting, that is the answer, 0.8009. That is the answer. So that's what I calculated over here. So that's how you can solve the examples based on this one. And then after, let's go for, I think these examples are more than enough, but if you want, I can go over one more example, and then after we can do the next thing. Okay, so now another example is example number 5. Which one? Let me take 66. 5.66. Okay, I think this is the last one. 5.66 says that, please try to, okay, let me again stop sharing and let me start my book so that you can read the example. 5.66. It says that changes in airport procedure require considerable planning. Arrival rates of aircraft are important factors that must be taken into account. Suppose small aircraft arrive at a certain airport according to a Poisson process at the rate of 6 per hour. Per hour, again Poisson, right? And Poisson process already mentioned over here, and the rate of 6 per hour means average rate of 6 per lambda equal to 6, lambda t equal to 1. Thus, the Poisson parameter for arrival over a period of hour is nu equal to lambda t, that is equal to 60. What is the probability that exactly 4 small aircrafts arrive during a 1 hour period? What is the probability that at least 4 arrive during a 1 hour period? Okay, exactly 4, at least 4 means 4 and greater than 4. If we define working day at 12 hours, what is the probability that at least 75 small aircrafts arrive during a working day, right? At least. So please keep this example in mind, and then after we can solve this example. Okay, so solution is something like this. It says that what is the probability that exactly 4 small aircrafts arrive over here. Okay, so 5 point, it is 66. Okay, already I mentioned here. So I would say that this A part is probability of x is equal to 4 and my lambda t is equal to 6 times 1, that is equal to 6. Please keep this thing in mind, right? And that is equal to, lambda is equal to 6 and xt, that, okay, that's fine. So I can write that is equal to summation of x is equal to 0 to 4 and e to the power lambda t you can use, or what, and p of x, p of x and lambda t. Am I right, guys? P of, what is the definition? P of x and lambda t. Yes, x and lambda t. Lambda t, that is equal to 6. So that is equal to x is equal to 0 to 4. And here I can write that is equal to p of x, and here it is 6. P of x and exactly 4 means, again, guys, let me just eraser. So let me erase this part, exactly 4. That means I'm going to do something like this, just like my previous example. So minus, this is equal to, let me write 6 here. That is equal to 6. And summation x is equal to 0 to 3, because here it is 4, 0 to 4, and here it is 0 to 3. So that is exactly equal to 4. So that's how it works. And here it is p and x and 6. So if you plug these values, or if you look at the table, you're going to get the answer that is equal to 0. If I can see over here on my book, the tabular form 0.1521, 0.1512, sorry, 1512. And if you subtract this one, you're going to get 1339. So that is my A part. My B part says that probability of x is strictly greater than or equal to 4 for lambda t is equal to 6. So that is equal to summation of 1 minus summation of, or let me write like this, summation of x is equal to 0 to x is equal to 4 to infinity, and p of x and 6, and that is equal to 1 minus summation of x is equal to 0 to 4, and here it is p and x is greater than p and x and 3, because greater than or equal to 4, so 4 is over here, so that means I would say that here it is 3. So x and 6, and if you write this one, you're going to get that is equal to 1 minus 0.1512, and that is equal to 0.8488. That's how you can get the second answer. My third answer is probability of x greater than or equal to now 75, and my lambda t is equal to 12 hours, right? So it is 6 multiplied by 12, that is equal to 72 hours. Okay, so that is equal to, again, the same thing, x is equal to 75 to infinity, and probability of x, and you can see over here lambda t that is equal to lambda t that is equal to 72, right? So that is equal to 72, and that is equal to, yes please, 1 minus summation of x is equal to 0 to 74, and x is equal to 0 to 74, that is my r, and here it is p of x and 72. And if you use your table again, you're going to get 1 minus, if you subtract this one, you are going to get, this is the answer. So that's how you can solve the examples. I think these examples are more than enough. These are more than enough things. So now let's go for the next part. So let me do one thing, guys, because this is the end of the chapter, so I don't want to continue with this one. Let me stop this recording, and we can start the new video. We can start a new video for our next chapter. So let me just save this one, and I would like to upload 2 videos over here. So this is, let me save in a folder, and yes, this one is done. And this is my article. Which one article? Poisson distribution, right? So examples, article 5.5, article 5.5 in the book. So 5.4, 5.5. So I would say 5.4, 5.5. Yes, example. 5.5 examples. So let me stop this one, guys. Stop sharing this one. Oops. Okay, I'll do it later. Okay, so let me stop sharing this one and